Good evening, ladies and gents, and welcome to the second in a series of three different basically exam coaching sessions that I'm doing for year 12. So yesterday we covered organic chemistry. So if you're watching a recording of this and you want to go and check out some hints, tips and hacks for organic chemistry, then go and check out my channel. This one, all about enthalpy, okay? All about enthalpy. So, and well, what are we doing tomorrow? And tomorrow is all about bonding. Now, those three topics, why those three topics? Well, I wanted to make this relevant for obviously year 12s and year 13s because on the analysis of all the past papers, okay, for A level, these are the top three topics that rear their head in your year 13 exam. So they're always going to sneak something like this in here for you. So like I said, yesterday we covered Year 12 organic chemistry for AQA, OCR, Edexcel, and WJEC. And tonight is no different. It's for all the exam boards. Enthalpy is enthalpy is enthalpy. Yes, the questions are slightly different, but you know, the Hess's law, calorimetry, okay, mean bond enthalpies, everybody has to do those, and they will crop up in your AS and A-level exams. I say your AS are done, but obviously a lot of you, most of you in year 12 are going to be doing internal exams, so this is in plenty of time to give you some hints and tips for that. So as always, I want this to be as interactive as possible, so please, when I ask questions, pop the answers in the chat for me, and also if you've got a question, then pop that in the chat, okay? So don't wait until I finish kind of rambling, just throw it in there and I will find it and come back to it, okay, folks? So enthalpy, what is that all about? We're going to be covering three major areas tonight, okay? So the first being just what enthalpy is, and then we're going to go straight into calorimetry. Secondly, we're going to look at mean bond enthalpies, and then thirdly, we're looking at Hess's law. And throughout all three of those, I'm going to be giving you my best hints, tips, and hacks, and you can use those to help you answer exam questions, because one of my things is that it's not necessarily what you know in A-level chemistry, it's what you can do. And it's about answering those questions, applying laws, applying principles, applying calculations, and so on and so forth. And when it comes to those calculations, any sort of calculations in A-level chemistry, the calculations themselves are not difficult. We multiply, we divide, we use some ratios, the odd kind of square root, okay? But essentially, it's about technique. Okay, and it's about methods. And if you've got a reliable method to help you through the different types of calculations that you need to be able to do, then that is the most important thing. As long as your method works, all right? Now, I'm going to show you some methods tonight. You might have a different method. Your teacher might have taught you differently. Whatever works for you. I'm not precious about these. I'm just giving you an alternative, maybe. I'm giving you something to think about. And obviously giving you some hints and tips, like we did yesterday with organic chemistry, to kind of support your thinking and your learning, if you like, as you go through these topics and as you revise for your exams. So without further ado, let's just get started. So enthalpy, what is enthalpy? Well, let's look at a cheeky little definition first and foremost. So enthalpy, so what is that? Let's start on the left hand side here, okay? It is the heat change at constant pressure, because enthalpy is all about the amount of energy inside a chemical system. That's what enthalpy is. But enthalpy change, okay, is the only thing we can measure. All right, think of this beaker here. Oh, come on, Rich, you can do better than that. Think of this beaker here as all the energy in a chemical system. Okay, now all the energy stored in a chemical system is within the bonds. All right, now when a reaction happens, there is bond breaking and bond making. There's a change of energy going on because, you know, a CC bond contains a different amount of energy to an O double bond O, and so on and so forth. So when a chemical reaction happens, which is essentially just a rearrangement of the atoms, breaking bonds and forming new ones with different atoms, there's going to be a change in energy. And that change in energy essentially comes from, or sorry, not comes from, but basically rears its head as a change in temperature. That energy change is it happens through thermal energy, okay? So it either releases heat energy, i.e. an exothermic reaction, or it absorbs heat energy overall, i.e. an endothermic reaction. So enthalpy change, known as delta H, and you can think of the H as standing for heat, that's absolutely fine. Delta meaning the difference. So it's the difference in heat change when a reaction occurs. So let's say a reaction occurs and energy gets put in to break bonds and energy gets released when bonds are made. Now that is a really fundamental fact that you can apply anywhere in A-level chemistry, okay? Doesn't matter what type of bonds they are. They could be ionic, metallic, covalent, could be any of your intermolecular forces. Wherever you have two things that are attracted to each other and you need to split them apart, then that requires energy. Energy goes in. Of course, when two things are attracted to each other, again, forming any type of bond or any type of interaction or intermolecular force, energy gets released, okay? So it can always kind of back you up in an exam if you're not sure what's endo and what's exothermic, what's positive and what's negative delta H. Just think, are two things coming together being attracted? In which case, negative delta H, exothermic. If you're pulling two things apart, like an ionization energy, for example, you're ripping an electron away from an atom. That requires energy. You need to put energy in to do that. So back to our little beaker. So if this is all the energy in a chemical system, and then a reaction happens, and at the end of it, okay, energy had been released. Let's say this is an exothermic reaction. Some of that energy overall stored in the chemical system has been lost to the atmosphere as heat energy. What's going to happen to the amount of energy in the chemical system? Well, overall, it's going to be less. If some of it was released as heat to the surroundings, then it's going to be less. Okay, so this is our chemical system again here. So you can see there's a difference. Okay, overall, it's lost energy from the chemical system. So this is, of course, negative. It's gone from here down to here. Okay, so that is a negative enthalpy change. And that's why, because it doesn't seem that kind of logical, does it? If temperature goes up, enthalpy is negative. Well, in this respect, when you think about it this way, it absolutely does make sense, okay? Because where did that energy come from? That heat energy, it came from the chemical system. So now there's less energy in the chemical system from when we started, hence a negative delta H. Of course, the opposite is true if we had an endothermic reaction. So if we had an endothermic reaction which absorbed heat energy from the surroundings, then the amount of chemical energy in the system has gone up. So that's why it's a positive delta H, okay? So just remember, exo equals a negative delta H, and an endothermic, where the temperature goes down and heat energy is absorbed from the surroundings, that is a positive delta H, okay? And like I said, breaking bonds, you need to put energy in, so that's a positive enthalpy change. Making bonds is exothermic, it's a negative enthalpy change, okay? So that's just a quick 5-minute kind of overview as to what enthalpy is, because I think it does get kind of skipped over a lot, really. You just go straight into it and never really pause to think about what enthalpy changes are and why we get these positives and negatives. So if you found that useful, that's great. Now, calorimetry, ladies and gentlemen, before we get into kind of Hess's law and stuff like that, calorimetry is one of those pracs that comes up a lot. And I've got a question pack for you, okay? And you can have a go at the questions in there from all the different exam boards, but you know what? They're all relevant for you to have a go at. So if you want to practice these types of questions, then please go ahead. And I'm just going to highlight some of the things to look out for in your calorimetry practicals. So what is calorimetry? Well, calorimetry is a method in chemistry whereby we can measure the enthalpy change for a reaction. Now they come under basically two types, okay? So we got two types of calorimetry prac. The first one is where we have, where we're trying to find delta HC, okay? Now delta HC is one of the two delta H's, or yeah, one of the two main delta H's that you need to know in year 12. There's enthalpy of combustion. One piece of advice, and I'm not going to go through them all here because you can just look them up. Know your enthalpy definitions, okay? That's so important because they'll give you equations and maybe ask you, what does this represent? What type of enthalpy change does this equation represent? The equation, okay, is the definition in equation form. okay? And of course, vice versa. They link to each other. So if you remember the definition, that can help you write the equation. For example, delta HC is the enthalpy change when, okay? So when your definitions, and I'll just put this up here, the enthalpy change when, TECU, all right? So always start any enthalpy definition with that. The enthalpy change when 1 mole of a substance is burned in excess oxygen in standard conditions, all right? So that 1 mole part, and of course, I say of course, but all enthalpy definitions have that 1 mole in there as well, okay? So 1 mole of a substance is burned in excess oxygen under standard conditions. So for example, CH4 as in methane gas reacts with excess oxygen in standard conditions to give carbon dioxide, gas, and water. Okay, and that's gas as well. And of course, we can balance it. So that's 2 waters, so we'll need 2 of those. Okay, so 1 mole of a substance is burned in excess oxygen in our standard conditions. So, you know, those are essentially what these are. Okay, maybe that's a liquid actually with it in standard conditions. But so the first enthalpy prac you're going to look out for is the one where we have a tin can. Okay, so I'm just going to draw our calorimeter like so. And then underneath we'll have a spirit burner, something like this. Excuse my rubbish drawing, guys. And this is where our fuel sits. And of course, that burns and we heat water. This is a known volume of H2O. And of course, we've got a thermometer in there as well, okay, measuring the temperature change. So if you see this, know that your job is to find how much energy is released from that fuel per mole, all right? So that's our delta HC prac. And so just when you first look at these questions, just think to yourself, right, what type of calorimetry prac is it? And you spot this spirit burner and you think, right, that's a fuel. This is made out of copper or tin or something like that. It's made of a metal. Why? Because this is all about getting as much of that heat energy that's being released by this reaction into the water. So we need something to conduct the energy into that water because that's what we're using for our calculation in order to find out how much heat energy was actually released. Now, the other flavor, if you like, or genre, is basically where we're finding a delta H reaction. Okay, now I say delta H reaction because this could be maybe a metal plus water, it could be a metal plus acid, it could be acid plus base, it could just be a salt dissolving in water. Okay, now the difference between these two is one reaction is happening outside the calorimeter. On the right hand side, this one's happening inside the calorimeter. So what we have is a polystyrene cup this time, okay, acting as an insulator. Why do we need an insulator? Well, because whatever reaction is happening, that reaction is happening inside the calorimeter, okay, inside the calorimeter. So my iPad's frozen, which is not helping, okay? I don't know why it's done that, probably because I got lots of PDFs open on here, okay? So let me just kind of come out of this for a second, and I'll just keep talking whilst I'm sorting this out. So the difference is the reaction is happening inside the calorimeter, okay? Inside the calorimeter. So rather than trying to get heat energy into it from an external source, any heat energy that's produced by the calorimeter, or by the reaction, sorry, we need to keep inside that polystyrene cup. So that's the difference. So it's acting as an insulator. We want to keep all that heat energy in there, okay? Now, just wait for this to come back up. And it's got rid of my drawing. That's not useful, is it? Okay, so I'll just do it again. Sorry about that, folks. Technical difficulties, and I'm not entirely sure why. Okay, so there we go. Let's go to line. Okay, so our calorimeter here, and you can always look back at this, okay? And there's our reaction happening in here, all right? So this is basically just a delta HR. And as I said, metal plus acid, metal plus water, something dissolving in water, just something that's happening in solution, essentially, okay? And of course, on the left-hand side, I'm just going to do a scratch drawing here to kind of pick this up. Okay, there's our thermometer. Obviously, we need a thermometer in here as well, and our heat coming from, oops, our spirit burner. Okay, our fuel there, like so. So like I said, first job, just know which one you're dealing with, looking at the question in front of you. And you know what? A lot of the time there is a diagram, so you can just spot it straight away, okay? But of course, when you read the question, if you're burning a fuel, you're definitely doing this. If it's anything else that's happening in solution, a reaction happening in solution, it's the one on the right-hand side. So how do we go about these questions? In the chat, what equation is synonymous with this? What equation do we think, right, it's calorimetry, this is the equation that we need to use? Pop that in the chat for me, guys, and we'll talk about how to go about this equation and how to use this equation and the things to look out for that might trip you up, okay? So don't be shy, just throw it in the chat. What is the equation that jumps in your head, that kind of particular bell ringing in your head as to what equation do we need to use in order to find our energy change for this reaction? Perfect, Harry, thank you so much. Okay, Q equals MC delta T. Okay, so MC delta T. Okay, so we have got a number of different things in here. Firstly, let's look at Q. What is Q? So if they ask you to find the energy change for the reaction, that is it. Now, I'll explain the difference between Q and delta H when we get to that, okay? But the energy change for the reaction is essentially just overall how much energy was transferred during this reaction, okay? And there's, regardless of how much fuel you used or what your reagents were and this, that, and the other. One thing I want you to remember is everything that goes into our MC delta T here is to do with either the water or the solution, okay, here or here. It's to do with the liquid. It's always about the liquid, because a really common mistake is this is mass, okay? But if they're using a solid or you're burning a fuel, and you very easily students say, oh, well, that's the mass. No, it's the mass of liquid, okay? And we tend to stick to 1 gram per centimeter cubed. So basically, if you've got 50 centimeter cubed of water in your calorimeter or 50 centimeter cubed of solution, this is 50 grams, okay? So you can assume, unless you're told otherwise, which is very, very rare, that this is your mass, okay? So this is essentially the volume of solution, okay? It's never the magnesium or the fuel or anything like that. It's just the water or solution. C is your specific heat capacity, okay? That is 4.18 joules per Kelvin per gram, okay? So that's essentially how much energy does it take, joules, to raise the temperature by 1 degree Kelvin or 1 Kelvin of 1 centimeter cubed of water, okay? So essentially, if you've got 1 centimeter cubed of water, how much energy does it take to increase the temperature by 1 degree or 1 Kelvin, all right? And then lastly, this is your delta T, of course. This is a change in temperature. Now that can be in Kelvin or degrees Celsius, it doesn't matter. Little tip for you is that where you've got temperature in an equation, just temperature, okay? Like in PV equals nRT, your ideal gas, that has to be in Kelvin, okay? Has to be in Kelvin. Whereas if you've got delta T, it doesn't matter, okay? The reason it doesn't matter, of course, 0 degrees Celsius equals 273 Kelvin. Now, of course, if you were to use 0 or 273 in your PV-nRT, then it's going to make a massive difference to your result, all right? Whereas if you've got delta T, it doesn't matter, because let's say this is 10 degrees, that equals 283 Kelvin. The difference between the two is the same. It's still just 10. So where you've got a delta T, it doesn't matter whether you're working in degrees or Kelvin, because they work on the same scale, they're just offset from each other, okay? An increase of 1 degree is an increase in 1 Kelvin, and so on and so forth. So just a little tip there for you. So this is all to do with your solution or your water, okay? Now the reason, I should say that Q always comes out in joules. The reason that comes out in joules is because of your specific heat capacity, Okay, your mass is in grams. Your temperature change, well, like I said, it doesn't really matter, but that's why it's there. So your answer for Q is going to come out in joules. Okay, so one way or another, you're going to be able to find these things in the question. It's going to give you the volume of solution. Obviously, your specific heat capacity is given as well, but I'm pretty sure you'd remember that's 4.18 if you've done this enough, like me. And of course, your temperature change. Okay, you're going to have to maybe calculate it. Maybe they'll give you a starting temperature and a final temperature, and you just have to find the difference. Easy enough. So once you found Q, that is the entire energy change for that whole reaction that's just occurred. After that, the second step is, of course, finding delta H. Now, delta H is always measured in kilojoules per mole. So the first thing we have to do, number one, is convert Q from joules to kilojoules. I just do it as a matter of course now. I find Q, I just turn it into kilojoules. Divided by 1,000 because I know I'm going to have to at some point anyway, okay? So you have to do that. Make sure your Q is converted into kilojoules. So your enthalpy change equals basically the entire energy change for the reaction that you've just done divided by number of moles. Now the big question, and again another huge area where students do lose marks on this, is not knowing which number of moles to use. So if it's delta HC, it's the number of moles of your fuel that gets burned, okay? And you can find that out because what they'll tend to do is give you the mass of fuel at the start, how much fuel was left at the end, and it's just the difference in mass there. And of course, once you've got the mass and you know the fuel that you're using, whether it's methanol or propanol or something like that, if you've got the formula, you can find number of moles, mass over molar mass. So that's the number of moles of your fuel. Now, if you've got one of these reactions here, okay, really importantly, if it's delta HR equals the number of moles of the limiting reagent. Okay, limiting reagent. Now, there's a number of different ways in which they can kind of how can I put this? Kind of guide you as to what the limiting reagent is. A lot of the time they'll say, oh, 0.02 grams of magnesium was added to excess HCl. Or, 1.2 grams of ammonium sulfate was added to, excess water or something like that if it's just dissolving. I've never seen a question where you have to calculate which is the limiting reagent, which is a skill that you need, but I've not seen it linked in any exam board to this. So there will be a clue in the question as to which is in excess. And of course, therefore, then the other one, the other reagent is your limiting reagent. Okay, so always just watch out for that. It's got to be the limiting reagent you use because it makes sense that, if you've got like 3 moles of one thing and, like 8 moles of another, if you and basically, like, if you use this number of moles, even though they don't all get used up, it doesn't make sense because some of that excess reagent didn't react. So you can't attribute any of that heat change to that excess reagent. Okay, so always find your limiting reagent because all of that reacted. All of that reacted because obviously it all got used up. So you can then attribute that number of moles to it, and that gives you your enthalpy change. Okay, so let me share with you this. Okay, so these are calorimetry questions. Now these are from all the different exam boards. Okay, now if you want practice with calorimetry questions, then I have got you. Okay, so you can see here delta H combustion practice. They tend to give you a table. Here's space for working. Here's another combustion one. This one here, magnesium reacting with zinc in a displacement style reaction, a redox reaction, happening in solution. That's going to be a different type, the one on the right hand side with the polystyrene cup, and so on and so forth. This one here, calculate the temperature rise when these two acid and base react together. That's going to be in your polystyrene cup. Okay, and again you can see here that, you know, we have to work out the limiting reagent. Okay, we have to work out the limiting reagent. So just watch out for those. You can download these. The mark scheme is on the end. Okay, so the mark scheme is on the end of this. Now, what time are we on? We are basically flying through. Okay, we haven't got more. I thought it'll only take 15 minutes. Here we are, 25 minutes later. So have a go of those. Watch out for, and this is something I'd recommend for every practical, guys. Okay, you've all got largely they're the same, but you've all got different required pracs that you need to know. Now, write this down. Okay, when you're revising required practicals, and this is for everybody year 12 and year 13, I'll be going through this next week in my exam training for year 13. 3 things you need to know for every practical, okay, or 3 things I recommend. And if you're going to create a cheat sheet, like a one side of A4, put these 3 things on there, because these are the 3 things that they ask you about. Number 1, your method, all right? Very rarely do they say, just write the method for this prac, okay? Very rarely. Maybe for making up a standard solution, that's probably the most common one. So your method, the reason being, because a lot of the time the exam boards like to give you questions like, oh, okay, like, I don't know, Joanne used this method for doing this practical, and what they'll say is, spot the errors in the practical. What could they have done differently to improve the accuracy or reliability or something like that? So if you know the method, then you can spot those differences. So the method is number 1. Number 2, calculations. Obviously, okay, know what you're doing with the calculations that follow. Q equals MC delta T is no exception. So knowing what you need to do there. And thirdly, errors. Common errors in the practical. Okay, so in terms of calorimetry, everything revolves around heat loss. Okay, getting the reaction to happen quickly is really important. Making sure you insulate that as much as possible. You know, heat loss to the surroundings is by far the biggest error. And what I'm going to say is consequential errors, I call them. They'll ask you questions like, oh, well, you know, Stephen was doing this practical, but, you know, he only burnt this fuel for like 10 seconds or something like that. What effect will that have on the delta H of the reaction, for example? So knowing what those consequential errors are, those common consequential errors, I haven't got time to go through them all here for you now, of course, but when you do those questions that I've just shared on the chat, then you will see what the common errors are and what the common answers are to those as well. Like I say, just because they're different exam board questions to the one you're doing doesn't matter. It's still just calorimetry. And in fact, doing other exam board questions for certain topics, okay, and that's where I'm looking after you here, will enhance your knowledge and make you more prepared for any questions, maybe let's say for AQA, that they haven't asked before, but maybe OCR have, you know. So bottom line, physical chemistry, so like anything to do with calculations, you're pretty safe doing other exam board stuff. Do not do it for organic chemistry. You're going to end up in a world of pain, okay? So physical chemistry, don't be afraid of using other exam board questions. So bottom line, calorimetry, spot your 2 types or one of your 2 types of practical. Obviously, just remember your Q equals MC delta T. You need to find the information in there. And then lastly, your delta H equals Q over N. Just watch what you're using for N. It has to be either your fuel or your limiting reagent inside that polystyrene cup, okay? And that's the one you have to use. So, like I said, use those questions wisely, okay? The answers are on the end. And you can practice those calorimetry questions. Basically, if you've done that entire booklet, and there's a lot of them in there, even if you've done half of that booklet and you're in a zone and you've got a reliable method of answering those questions and doing those calculations, then you're in a really good place. There'll be no surprises in your test or exam this year if you can get, you know, half of those right as you're working through them. So that'd be my recommendation, folks. Any questions, pop them in the chat. Otherwise, I'm going to be jumping on to mean bond enthalpies in a second. Now, mean bond enthalpies are a bit of a weird one. They tend to crop up more at AS, but I have seen them in A-level practicals. Enthalpy as a whole comes up a lot in A-level practicals. It's mainly calorimetry and Hess's law, of course, but I'm going to put this in here, obviously, for the year 12s because it's year 12 content. And I want to help you guys out. So, mean bond enthalpies. I'm just going to dive straight in on a question because I'm going to show you my method for calculating mean bond enthalpies. You might have your own. That's absolutely fine. But you know what? This method has never, ever let me down. Okay, so I'm just going to jump straight into that. So, typical questions. Okay, so these are all AQA questions. What else we got here? This is an OCR one, OCR. Then we get to Edexcel. Okay, so there's loads of different questions here, and again, answers as well. In fact, you know what? Whilst I think about it, I am just going to pop that in the chat so you can download it, folks. Boom. There you go. So, how do we go about these? Well, as I mentioned right at the top, the thing that you always need to keep in your mind when thinking about bonding and enthalpy is that bond breaking is endothermic. You're literally pulling two things apart that are attracted to each other, positive and negative, okay? Whether it's covalent, whether it's ionic or whatever. So anytime you're trying to separate things, that's endothermic. You put energy in, so it's a positive enthalpy change. When you make new bonds, that means energy gets released. It's almost like when a new bond forms between something positive and something negative, then it's almost like a sigh of relief that the compound has, and it's kind of like, oh, thank goodness for that. You know, I needed an extra couple of electrons to satisfy my outer energy level, and it's kind of like, just think of them like breathing out energy and they're settling down and they're stabilizing, okay, and they release energy as a consequence. So this one, I'm literally just going to go for the first one. So hydrogen fluoride reacts with ethine, C2H2, which it's not in the spec, but that doesn't matter because we've got all the information to deal with it. All compounds are in the gaseous state. Now that's important because that's part of our definition of mean bond enthalpy. So the definition of mean bond enthalpy is the, as we mentioned before, the enthalpy change when, okay, 1 mole of a particular bond, okay, is broken in gaseous conditions, okay? That's really important, that gaseous bit. If they ask you what mean bond enthalpy is, be sure it's 1 mole of a bond, okay? So the enthalpy change when 1 mole of a particular type of bond is broken in the gaseous conditions. So what they've done here is give you the displayed formulae of all the reactants and products. If they don't do that, 100% I recommend that you do that. In fact, let's just find one where they haven't, okay? Let's just use this one, okay? So we got the combustion of ethene, okay? And we've got the reaction here, okay, balanced, and we've got the delta H for the reaction. When you practice these, you probably practice them trying to find the delta H of the reaction. 9 times out of 10, folks, they're not asking you to find the delta H for the reaction. They're asking you to find the mean bond enthalpy of one thing. So here, they're asking you to find the mean bond enthalpy for C double bond C, all right? So the way I recommend this, doing these, is as follows. So if they haven't given you the displayed formulae for each of these, draw them out, because one of the biggest sources of error for these is miscounting the number of bonds that you have, all right? So C2H4, of course, that is ethene, like so, plus 3 O2s. So I've got O2, knowing that, that's important, it's a double bond, and of course 2 CO2, and that's what CO2 looks like. So we can see the bonds here, and then 2 waters, so just 2 lots of H2O. Now we can see all the bonds. Now, I get students come to me all the time and say, oh, is it products minus reactants or reactants minus products? It's like, and you know what? It's just so easy to forget that. You've got no basis to kind of back you up and work that out. So what I recommend is 100% that you remember that all bond breaking is endothermic. All bond making is exothermic. So every number I put over here on the left-hand side, because I'm breaking every single bond, is positive. Every number that I put over here, because I'm making bonds, is negative, okay? So let's just top these up. So we've got a C double bond C. Now, if you do have an unknown, okay, in an unknown bond, like you're trying to calculate here, call it X, okay? But if there's more than one of them in this equation, then it'd be 2x or 3x or 4x, okay? Here I've only got one, so I'm just going to call that X. I've got 4 CHs, so that'll be 4 times 413. And I've got, 3 O double bond O's, so that's 4 times 498. Okay, so I'm basically just going to keep those as they are. On the right-hand side, I have basically got minus 4 times C double bond O, so that's minus 4 times 805. Notice I'm putting a minus in front here, guys. And then minus 4 times OHs in my waters, so that is 464. Okay. Now, literally, if you were just working out delta H, you just line these up, okay, as if you were calculating delta H. So that's what I'm going to do, actually. I'm going to put this minus 1318, minus 1318, that's our delta H, okay, equals X plus 4 times 413 plus 3 times 498, and then we get to the minuses. Minus 4 times 805, minus 4 times 464. Okay, so if you were calculating, if you needed to know that and you had a number for that X, then literally all you're doing, you don't have to remember products minus reactants or whatever. Literally just line up all the values that you've listed on the left hand side and the right hand side. Does that make sense, guys? I've not got much. I mean, Harry's obviously kind of chipped in earlier on, but I've not got much from people in the chat here. So does that make sense, guys? The way I've done that, okay, bond breaking, positive, bond making, negative, and then just line them up. Yeah, there's nothing else to remember there. Is that helpful? Beautiful. Thank you, Suman. So we are trying to find X here. Now, once you've got it like this, it's really easy to rearrange, okay? So you want to make X the subject. You literally just have to move everything over to the left-hand side of that equal sign. Obviously, flipping or inverting the signs, okay? So it'll be minus 4 times 413, minus 3 times 498, plus 4 times 805, plus 4 times 464, minus 138, and that will just give you X. Okay, so my advice is when you do these, just set it out. Even if you do know delta H, set it out with delta H for the reaction as your subject, and then rearrange. Okay, because the thing is here, ladies and gents, is that as I mentioned before, the calculation is not hard. You lose marks by missing little things. So a simple and reliable method for doing these practicals is the way forward. Something that gives you the correct answer 100% of the time. That's what we need with these sorts of things. Now, like I said before, you might have a different method for that. That's absolutely fine. But if you haven't got a reliable method and you are still using that, I don't know, I don't even know whether it's reactants minus products or products minus reactants, whatever, because that's the method I use and it just works every single time. Just need to look after your numbers, okay? So take your time, especially when calculating it. Take baby steps if you need to. That's how I tend to do things to minimize mistakes, and you will get the correct answer, okay? The biggest mistakes that come in are miscounting bonds, or just like entering some of the stuff in your calculator, or just rushing. Okay, so just slow and steady wins the race when it comes to these. They're not complex calculations, but they contain a lot of numbers, and that's where errors can creep in, folks. Okay, so when you look at an exam and there's a mean bond enthalpy question in there, you should be all over it. Okay, it's easy money. All right, as long as you've got a reliable method. So any questions in the chat, guys? You pop them in there. That's absolutely fine. I will answer those. But essentially, like I say, in here, we have got a rook of different bond enthalpy calculations, okay? And of course, all the answers at the end there for you as well, okay? So you can see here the average number of marks, 4 marks, 3 marks, 3 marks, 3 marks, 2 marks because it's a tiny one. That was worth 3 marks as well. So 3 or 4 marks, there you go, there's a 4 marker there. 4 marker there. So, that's not a bad a number of marks for what is relatively an easy calculation. Okay. Sweet. So we come to the really fun bit, and that is Hess's law, of course. Okay. So Hess's law is, hugely important. okay? Not just generally speaking in chemistry, but hugely important for you guys because you know what? It's definitely going to be in your end of year exams for year 12. And I'm sure at some point, either in paper 1 or kind of maybe paper 3 or something like that in your A-level exams, Hess's law will need to be applied, all right? So here's my kind of brief introduction to what Hess's law is, okay? And the definition, again, is really useful. It's not one of those that they ask, okay? So it's never really an exam question itself, but it's worth kind of knowing so it can help you kind of decide like what's going on in a reaction. So in terms of Hess's law, let's use, it's not writing red, okay? So Hess's law, so the enthalpy change, I'm just going to use delta H. The enthalpy change for a reaction is independent of the route taken. I think that's the nicest, kind of most succinct kind of version of Hess's law, okay? So what we're saying is, let me just give you an example, and I may be preaching to the converted here, okay? If we can't find by calorimetry this delta H, okay, there may be lots of reasons why we can't just react A and B together to make C and D and measure that delta H directly like we looked at in calorimetry. Reasons include the reaction is too slow, the reaction is too fast, the reaction isn't exothermic enough, the reaction is too exothermic. Maybe we need to heat these reactants to get them to react in the first place, in which case if we've got a Bunsen burner kind of plowing in heat energy, the thermometer is not really going to give us a very accurate result for how much energy gets released or absorbed by that reaction because we're just heating it with the Bunsen burner. So there's lots of different reasons why we can't find delta H for a reaction directly. It might be that the reaction just doesn't happen in standard conditions. You know, if you took a kind of belt, like a jar, okay, like a gas jar from the lab, and you put some carbon in the bottom, maybe some graphite, okay, and then pumped a load of oxygen and hydrogen in there and just kind of give it a shake. I mean, are you going to make methanol? Are you going to make an ester? Are you going to make carbon dioxide? Are you going to make water? Like, you've got 3 elements in there, and there's like almost unlimited things you can make out of it. So the reaction just wouldn't happen under standard conditions. There's not enough energy for that reaction to happen to make a product. So there's loads of different reasons why we couldn't measure that directly, okay? So that's why we look for an alternative route. So down here, this is our alternative route, and we call this our intermediates, okay? So if we can find a delta H reaction for A to something else, and B to something else, and then from that something else to C and something else to D, the energy change, the sum of these energy changes, okay, equals delta H. Okay, so that's what Hess's law is. We're just looking for an alternative way around, okay? So they would equal each other. That's what Hess's law is. Now, year 12s, all right, there are, again, 2 types of questions that I want you to look out for when it comes to Hess's energy cycles, okay, and Hess's law. The first one is where they give you data for delta HF. Delta HF is delta H formation. The enthalpy change when 1 mole of a substance is formed from its constituent elements in standard conditions, okay? Now, where you've got delta HF values, all right, that means, you know, you are forming those products, all right? It's all about the data in the table that they give you, and they will give you a table of values, okay? Now, the type of values they give you, the enthalpy values that they give you, is what dictates how you're to go about this question. So if they give you delta HF values, okay, where you're forming things from their constituent elements, then let me show you. So let's say we've got a reaction at the top here. Let's just use a combustion reaction. So methane goes to CO2 and water. Well, let's quickly balance. Okay. Now, we can't measure maybe this delta H reaction. I mean, we probably could, but you know, the point is that we can't, you know, in theory. Now, if they give you delta HF values for methane, for oxygen, for CO2, and for H2O, well, not for oxygen, because delta HF is the formation of a substance from its constituent elements. So if you have any element in its standard state, it does not have a formation value. Because, you know, what's the energy change when oxygen gets turned into oxygen? Zero. Like, it's already oxygen. There just isn't a change, is there? Okay, so that's why. So if they give you delta HF values, what goes in your intermediate box? Well, in your intermediate box, you have your elements in their standard state. So essentially, you've got carbon as a solid, you've got hydrogen as a gas, and you've got oxygen as a gas as well, because those are the elements that make up both sides of the equation. Now, if they give you delta HF values, okay, it's arrows up, all right? So we are forming methane from carbon and hydrogen. We are forming carbon dioxide from carbon and oxygen. We are forming water from hydrogen and oxygen, okay? So let's say they give you some values here, okay? So I'm going to call this X, Y, and Z. Just think of those as values, okay? Now, they've given us those values for the delta H formations. Now, how we actually put those numbers together, because we know that the sum of these equals this, but it's not quite so simple, all right? So we've got formation, arrows up. Now, our job is to get, let's use a different color, let's use this blue here. Our job is to get from the reactants down through our intermediates and back up the other side, okay? That's our job, okay? That's our alternative route. Now, you can see over here we have a problem. The problem is that, let me just get rid of that, and we go in through here like so. The problem here is that this arrow is going in the wrong direction, all right? It's like running up a down escalator, all right? It obviously in real life actually doable with a bit of effort, but you know, it's going the wrong way for us, okay? So what we need to do is flip that arrow. And luckily for us, because of Hess's law, you know, whenever a bond is broken, okay, and whenever a bond is formed, obviously, as we mentioned before, it's exo and endothermic, okay? Endo and exothermic, that way around. But they're equal and opposite in terms of values, okay? So because we're flipping this arrow the other way, this becomes minus X. If it was already negative, that number, you'd make it positive. So if you're flipping an arrow, you're flipping the sign, okay? So over here, they're going the way we want them to go. They're going towards our products, which is great, okay? So we don't need to do anything to those. So in this respect, the delta H for this reaction equals minus X plus Y plus Z. So again, a reliable method of doing this. And what you'll find is that whenever you have got delta HFs, it's always the arrows on the left-hand side you're going to need to invert, okay? Really, really important. It's always the left-hand arrows you need to invert. So that's where you've got delta HF values, okay? So arrows up. Just remember, you're going to need to invert one or more arrows on the left-hand side, and then you literally just put the numbers in. Of course, you do need to account for the number of moles as well, okay? This is the only one we really need to pay attention to, so that'll be 2Z, if you like, because we're making 2 moles of water. So you do need to take into account your number of moles in the equation as well. Now, secondly, the other flavor, if you like, of Hess's law question they can give you is for delta HC. Okay, so let's say we've got a reaction between sodium and chlorine to make sodium chloride. Does happen. Okay, so there's our balanced equation. But this time they've given you delta H combustion values. Okay, so delta H combustion, as we mentioned before, is the enthalpy change when 1 mole of a substance is burned in excess oxygen in standard conditions. So here, you don't need to write them, to be honest with you. It's just the oxides of the elements. So sodium oxide and whatever the oxide of chlorine is, like, is it chlorate or something like that? So this time, because enthalpy of combustion is the enthalpy change when a substance reacts with oxygen to form the oxides, it's arrows down, ladies and gentlemen, okay? Arrows down. So again, our job is to get from the left-hand side to the right-hand side like so. Okay, so again, let's go with W, X, and Y. This is 2Y because it's 2 there, and this is 2W because there's a 2 there. Now, if we want to find this delta H, which arrow do we need to invert? Which arrow is our kind of down escalator that we need to go up? Well, it's this one, okay? So we need to invert that arrow, so that becomes negative. But of course, if it was negative, we make it positive, okay? So when we flip an arrow, we flip the sign. So in this case, delta H equals 2W plus X minus 2Y, okay? And then that will give you your delta H for the reaction. So very quickly in summary, if you see a delta HF, if you get delta HF data, arrows up, flip the arrows on the left. If you get delta HC data, arrows down, flip the arrows on the right, okay? And you just can't go wrong. They're basically almost the only type of Hess's law question you're going to come across in terms of AS or year 12 certainly, but they do crop up obviously in year 13s as well. Now let me show you what can be confusing. And you know what? I mean, you guys probably already know by now that the exam boards are in the business of just making things a little bit more difficult for you. And it really annoys me, right? Because chemistry is difficult anyway. Without them kind of messing around, kind of trying to, change the context of the question or make it like really hard to comprehend what's going on. But, they're testing your ability to assimilate information and use it. What they will do is this. Let me show you. Let's find the right example here. So, not that one. Oh, yeah, okay. So this question here looks like a very simple one, 3 marks. Table 2 gives some values of standard enthalpies of combustion. Here, we got the substance, carbon, hydrogen, and hexane, okay? Use the data in table 2 to calculate the enthalpy change for the reaction represented by this equation. Now, this equation here is a delta HF. It is the formation of hexane from its element in its standard conditions. And sometimes they say that, use the data in the table to calculate the enthalpy change of formation of hexane, all right? Actually, they haven't done that there. Where have they done it? Oh, here. There we go. So the equation for the complete combustion of cyclohexane is shown below. So that is the combustion of cyclohexane, 1 mole of a substance reacting with excess oxygen. Standard enthalpy changes of formation are shown in the table. Calculate the standard enthalpy of combustion of cyclohexane. So they've mentioned both combustion and formation here. So what do we do? What do we use? Do we use formation and arrows up, or do we use combustion and arrows down? Answers in the chat, please, guys. Formation, are we using formation, arrows up, or are we using combustion, arrows down? So up or down in the chat, please, guys. What are we using here? Arrows up or arrows down? Arrows up for formation, arrows down for combustion. Let me know what you're thinking in the chat there, because they're just trying to confuse you here. So pop it in the chat. I'm going to have a quick drink. Formation up or combustion down? Arrows down, says Suman, or tentatively arrows down? Question mark. Anybody else want to chime in at this point? I know there's more than just Suman in here. Harry, you still with us? What are you thinking? Is it arrows up or arrows down? Get one more person chatting in on this. Alice says up. Hey, Alice. So we got 1 vote for down, 1 vote for up. It is arrows up. Now, the reason for that, and the reason I'm telling you this, is because they're just trying to confuse you. Pay no attention to the top equation. Pay no attention to what type of reaction that is. It doesn't matter. It could be a neutralization. It could be a combustion. It could be a formation. It could be something that we can't even label, all right? Pay no attention to it. And they've mentioned, combustion twice here, and even put the delta HC. Now, yes, that might be the equation for the delta H combustion of cyclohexane. We don't care, because all we're concerned about is the data in the table, okay? So whatever delta H data they give you, that's what you're focusing on, okay? So if you see delta HF data, it's arrows up. If you see delta HC data, it's arrows down, regardless of what that top equation is, okay? And that's what they'll do to try and confuse you. This is an OCR one, but I've seen all the exam boards do it. So, like I said, don't fall into the trap, all right? Yeah, blah, blah, blah. I don't care what reaction that is. Where's my data? What's my data? That tells me what to do in this case, okay? So hopefully that makes sense to you guys. I'm just kind of giving you a heads up as to kind of like, you know, what can possibly go wrong when you're doing these reactions. Now, a couple more things I want to touch on. We've only got 5 minutes left. Number one is if they ask you, I'm on the wrong sheet here. Remember in mean bond enthalpies whereby, looking at the wrong sheet again. Sorry, guys. We were looking at, where's the question? There it is. So I suggested to you, okay, lay out your calculation as if this delta H is the subject to start with, okay? Now, yes, in Hess's law questions, they can ask you to find that enthalpy change for the top reaction. But just like here, there was asking you to find that average bond enthalpy for a C double bond C, so it's just one of the things underneath. They can also do that with Hess's law, okay? So they could give you this delta H at the top here and ask you to find Y, all right? Now, again, same principle as mean bond enthalpies. Set out your equation, even though you know this number, set out your equation with that as your subject because that's reliable, okay? Once you've inverted which arrows you need to and stuff, that's reliable. If they were asking you to find Y, once you've got it set up like this, you then do your rearranging and take these other things to the other side to leave that as the subject, okay? So that's really, really important. It's about like logical steps, minimizing the risk of making a mistake, because I'm sure you're all really sharp. I'm sure you can all do multiplications and divisions and you know, ratios and stuff like that. Mistakes creep in when you try to do too many things in one go, okay? So my advice is be really kind of systematic with the way you go about these questions. Look after the numbers, okay, and your signs, and you can't go wrong, okay? So like I said, a reliable method. Last thing. These are all AS questions, by the way. I haven't shared these with you yet. Let's do that right away before I forget. So these, again, are all from different exam boards, but you know what? Perfectly doable for all of you, and you know, plenty of practice for Hess's law, and of course there are the mark schemes on the end there for you. Stuff like this. Some enthalpy data are given in the table. So we've got the enthalpy change for this reaction between nitrogen and hydrogen to give ammonia. Nitrogen to nitrogen N2 gas to 2N gas, and H2 gas to 2H gas. Use the data to calculate the bond enthalpy for an NH in ammonia. I'm like, okay. This is neither, and this is why in here, if you see a triple kind of exclamation mark, this is about constructing Hess's cycles from unknowns. And if AS people and your teachers are feeling mean in your end of year exam, they'll put one of these in. Watch out for these in A-level year 13s, okay? The piece of advice I want to give you for these, because it's neither delta HF nor delta HC, is you need to look for commonalities between the equations, okay? Notice how there's an N2 here and an N2 here. There's a H2 here and a H2 here, okay? I would recommend, obviously, you know, you need to try and put these equations together somehow, okay? Put these equations together somehow. So I'm going to go N2 plus 3H2 gives 2 NH3. Now, that's that one sorted. That's written at the top. Now, how do I construct these around it? Well, basically what I'm doing here, if you think about it, I'm taking an N triple bond N and I'm breaking that bond to make 2 separate nitrogen atoms. Same here for H2. I'm just breaking that covalent bond to make 2 separate hydrogen atoms. Now, these bits don't fit, okay? but these bits do. So I can say, okay, I'm going from nitrogen to 2 single N atoms. So going down here to 2N, and I can go down here, and these are our intermediates, by the way, to make, well, 6H, isn't it? Because we've got 3 there, okay? Now, these are the individual atoms we need to make 2 lots of ammonia. So what we can do is actually we can find this, okay, like so. Now we're going to need to find that over here. This is our question mark, okay? So I'm going to call this, because it's after the bond enthalpy for NH in ammonia. So if I took this NH3 and broken all 3 NH bonds, that's what they're after. How much energy does it take to break one NH bond? So I'm going to call this 6x. The reason being, because I've got 2 NH3s. Each NH3 contains 3 NH bonds. So that's why I've called that 6x, because all in all, I've got 6 NH bonds. So you can see how I've used this top equation at the top. I've used these 2 equations to create these here, okay? And this is our missing value, okay? So, you know, think of it like we're breaking bonds to make individual atoms at the bottom down here. So again, we know the delta H at the top here is minus 92. We know that this N2 is plus 944, and this H2, it is 3 times plus 436, and this is basically 6x, okay? So essentially minus 92 equals plus 944 plus 3 times 436. Now, of course, I need to invert this, okay? So that's going to be minus 6x, okay? Minus 6x, because I've inverted that arrow, because we need to get from here through to here, okay? So that's why I've done that. So all, again, we need to do here is basically make that the subject. I'd try and make it positive if I were you, okay? I'd try and make it positive by moving it to this side and then moving the 92 over here. But then, of course, to find an individual NH bond, then you just need to divide by 6 at the end once you found 6x, okay? So these are tricky, folks. These are really tricky. So there's one there. There's one here, okay? So this one you need to kind of think on your feet a little bit as well. And there's a third one, I think. Yeah, there it is. Okay, so there's another one there. So they're what I call using Hess's law with unknowns. My advice is look for commonalities between the equations that they give you. It's like putting together pieces of a jigsaw. That's all I can really say, to be honest with you folks, okay? So that's enthalpy, all right? Those are the things that I want you to look out for. All in all, know what enthalpy is, okay? Know your definitions, because they're really important. They can help you write equations, okay? And spot what type of enthalpy change an equation is, all right? So know those off part. Always start with the enthalpy change when, and there's always 1 mole of something going on there as well. When it comes to calorimetry, obviously know your calculations and know what you're looking for. Watch out for that limiting reagent for the N with delta H equals Q over N. When it comes to mean bond enthalpies, I've shown you a really kind of simple, kind of foolproof method. Not that you're fools, but obviously things can go wrong. We've all done it. We've made these stupid errors in an exam that made you go like, why? Just why have I done that? That's just ridiculous. You know, like you just, yeah, these things happen. Minimizing mistakes and just making sure that you just do things step by step, do things logically, look after the numbers, have a reliable method. And then lastly, Hess's law, okay? Watch out for those, delta HF, delta HC, but of course, watch out for the devil in there. That is those crazy unknown ones, all right? Alice, that's very kind of you. Thank you very, 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 very much. So if any of you are year 13, I'd love to see you next week if you haven't already registered. Yes, it does cost cash money, but you know what? This is basically this is just like a amuse-bouche, a little taster, if you like, as to what we're doing next week. It's all different, of course. We're focusing on year 13 stuff, but equally, if you're year 12, you're very welcome. Next week's not for you, but tomorrow we're going to look at bonding, and I'm going to change the way you think about bonding and bonding questions, okay? Because a lot of marks are lost because you say lots of things, lots of students write lots of things about bonding questions and answering bonding questions, but just missing the marking points. So my job tomorrow is to give you an idea of what those marking points are, and of course, how to nail them down. So I'll have more question packs for you and stuff like that tomorrow. In the meantime, look after yourselves, okay? If you are revising, take time for yourself. It's really important to look after yourself, okay? Because it's all about that, okay? You're no good to anybody if you're burnt out, okay? You can only do what you can do, and then you can be proud of that at the end. Okay, guys? So enjoy the rest of your evening. Thank you so much for coming along, and hopefully I'll see you either tomorrow or Year 13s next week in exam training, okay? And there's loads you're going to learn next week in exam training, so register for that. All right, take it easy, guys. Thank you again.